functions defined within the scope of other functions. We'll also look at the related concept of... Hello, my name is Austin Bingham, and welcome to the third module of Python Beyond the Basics. In this module, we'll look at local functions, that is, functions defined within the scope of other functions. We'll also look at the related concept of closures, which are key to really understanding local functions, and we'll close off the module with a look at Python's function decorators. As you'll recall, in Python, the def keyword is used to define new functions. Def essentially binds the body of the function to a name in such a way that functions are simply objects like everything else in Python. It's important to remember that def is executed at runtime, meaning that functions are defined at runtime. Up to now, almost all of the functions we've looked at have been defined at module scope or inside classes, in which case we refer to them as methods. However, Python doesn't restrict you to just defining functions in those two contexts. In fact, Python allows you to define functions inside other functions. Such functions are often referred to as local functions, since they're defined local to a specific function's scope. Let's see a quick example. Here we define a function sort by last letter, which sorts a list of strings by their last letter. We do this by using the sorted function and passing last letter as the key function. Last letter is defined inside sort by last letter. It is a local function. Let's test it out. Just like module-level function definitions, the definition of a local function happens at runtime when the def keyword is executed. Interestingly, this means that each call to sort by last letter results in a new definition of the function last letter. That is, just like any other name bound in a function body, last letter is bound separately to a new function each time it's called. We can see this for ourselves by making a small modification to sort by last letter to print the last letter object. If we run this a few times, we see that indeed each execution of sort by last letter results in a new last letter instance. The main point here is that the def call in sort by last letter is no different from any other name binding in the function, and a new function is created each time def is executed. Local functions are subject to the same scoping rules as other functions. Remember the legb rule for name lookup. First the local scope is checked, then the enclosing scope, next the global scope, and finally the built-in scope. This means that name lookup in local functions starts with names defined in the function itself. It proceeds to the enclosing scope, which in this case is the containing function. This enclosing scope includes both the local names of the containing function as well as its parameters. Finally, of course, the global scope includes any module-level name bindings. You can see this in a small example. Here we define the function inner local to outer. Inner simply prints a global variable and a few bindings from outer. This example shows the essence of how the legb rule applies to local functions. If you don't fully understand what's going on, you should play with this code on your own until it's clear. It's important to note that local functions are not members of their containing function in any way. As we've mentioned, local functions are simply local name bindings in the function body. To see this, you can try to call a local function via member access syntax. The function object outer has no attribute named inner. Inner is only defined when outer is executed, and even then it's just a normal variable in the execution of the function's body. So what are local functions useful for? As we've seen, they're useful for things like creating sorting key functions. It makes sense to define these close to the call site if they're one-off specialized functions. So local functions are a code organization and readability aid. In this way, they're similar to lambdas, which, as you'll recall, are simple, unnamed function objects. Local functions are more general than lambdas, though, since they may contain multiple expressions and may contain statements such as import. Local functions are also useful for other, more interesting purposes, But before we can look at those, we'll need to investigate two more concepts: returning functions from functions and closures. As we've just seen, local functions are no different from any other object created inside a function's body. New instances are created for each execution of the enclosing function. They're not somehow specially bound to the enclosing function, and so forth. Like other bindings in a function, local functions can also be returned from functions. Returning a local function does not look any different than returning any other object. Let's see an example. Here, enclosing defines local func and returns it. Callers of enclosing can bind its return value to a name, in this case lf, and then call it like any other function. This ability to return functions is part of the broader notion of first-class functions, where functions can be passed to and returned from other functions, or, more generally, treated like any other piece of data. This concept can be very powerful, particularly when combined with closures, which we'll explore in the next section. So far, the local functions we've looked at have all been fairly boring. They're defined within another function's scope, but they don't really interact with the enclosing scope. However, we did see that local functions can reference bindings in their enclosing scope via the LEGB rule. Furthermore, we saw that local functions can be returned from their defining scope and executed in another scope. This raises an interesting question. How does a local function use bindings to objects defined in a scope that no longer exists? That is, once a local function is returned from its enclosing scope, that enclosing scope is gone, along with any local objects it defined. How can the local function operate without that enclosing scope? The answer is that the local function forms what is known as a closure. A closure essentially remembers the objects from the enclosing scope that the local function needs. It then keeps them alive so that when the local function is executed, they can still be used. One way to think of this is that the local function closes over the objects it needs, preventing them from being garbage collected. Python implements closures with a special attribute named dunderClosure. If a function closes over any objects, then that function has a dunderClosure attribute which maintains the necessary references to those objects. We can see that in a simple example. The dunderClosure attribute of lf indicates that lf is a closure, and we can see that the closure is referring to a single object. In this case, that object is the x variable defined in the function that defined lf. So we can see that local functions can safely use objects from their enclosing scope, but how is this really useful? A very common use for closures is in so-called function factories. These factories are functions that return other functions, where the returned functions are specialized in some way based on arguments to the factory. In other words, the factory function takes some arguments. It then creates a local function which takes its own arguments, but also uses the arguments passed to the factory. The combination of runtime function definition and closures makes this possible. A typical example of this kind of factory creates a function which raises numbers to a particular power. Here's how the factory looks. Raise2 takes a single argument, exp, which is an exponent. It returns a function that raises its arguments to that exponent. You can see that the local function raise2exp refers to exp in its implementation, and this means that Python will create a closure to refer to that object. If we call raise2, we can verify that it creates this closure. We can also see that square does indeed behave as we expect. And we can create other functions the same way. The use of local functions raises some interesting questions regarding name lookup. We've looked in some detail at the LEGB rule, which determines how names are resolved in Python when we want the values to which those names refer. However, LEGB doesn't apply when we're making new name bindings. Consider this simple example. When we assign to message in the function local, what precisely is happening? In this case, we're creating a new name binding in that function's scope for the name message to the string local. Critically, we are not rebinding either of the other message variables in the code. We can see this by instrumenting the code a bit. Now we're actually calling the functions enclosing and local. Again, local is creating an entirely new name binding which only applies in the context of that function. If we run this code, we'll see that neither the global nor enclosing bindings for message are affected by calling local. In earlier courses, we've discussed Python's global keyword. Global can be used to introduce a binding from the global scope into another scope. So in our example, if we wanted the function local to modify the global binding for message rather than creating a new one, we could use the global keyword to introduce the global message binding into local. Let's do that and see the effects. First, let's use the global keyword to introduce the module level binding of message into the function local. If we run this, we can see that the module level binding of message is indeed changed when local is called. Again, the global keyword should be familiar to you already. If it's not, you can always review Module 4 of the Python Fundamentals course. If global allows you to insert module-level name bindings into a function in Python, how can you do the same for name bindings in enclosing scopes? Or, in terms of our example, how can we make the function local modify the binding for message defined in the function enclosing? The answer to that is that Python also provides the keyword non-local. Non-local inserts a name binding from an enclosing namespace into the local namespace. More precisely, non-local searches the enclosing namespace from innermost to outermost for the name you give it. As soon as it finds a match, that binding is introduced into the scope where non-local was invoked. Let's modify our example again to show how the function local can be made to modify the binding of message created in the function enclosing by using non-local. Now when we run this code, we see that local is indeed changing the binding in enclosing. It's important to remember that it's an error to use non-local when there's no matching enclosing binding. If you do this, Python will raise a syntax error. You can see this if you add a call to non-local in our function local, which refers to a non-existent name. When you try to execute this code, Python will complain that no such name does not exist. Like global, non-local is not something you're likely to need to use a lot, but it's important to understand how to use it for those times when it's really necessary, or for when you see it used in other people's code. To really drive it home, let's create a more practical example that uses non-local. In this example, the makeTimer function returns a new function. Each time you call this new function, it returns the elapsed time since the last time you called it. Here's how it looks. And here's how you can use it. As you can see, the first time you invoke t, it returns nothing. After that, it returns the amount of time since the last invocation. How does this work? Every time you call makeTimer, it creates a new local variable named lastCalled. It then defines a local function called elapsed, which uses the non-local keyword to insert makeTimer's binding of lastCalled into its local scope. Elapsed then uses the lastCalled binding to keep track of the last time it was called. In other words, elapsed uses non-local to refer to a name binding which will exist across multiple calls to elapsed. In this way, elapsed is using non-local to create a form of persistent storage. It's worth noting that each call to makeTimer creates a new independent binding of lastCalled, as well as a new definition of elapsed. This means that each call to make timer creates a new independent timer object, which you can verify by creating multiple timers. As you can see, calls to T1 have no effect on T2, and they are both keeping independent times. Now that we've looked at the concepts of local functions and closures, we have what we need to finally look at an interesting and useful Python feature called the decorators. At a high level, decorators are a way to modify or enhance existing functions in a non-intrusive and maintainable way. In Python, a decorator is a callable object that takes in a callable and returns a callable. If that sounds a bit abstract, it might be simpler for now to think of decorators as functions that take a function as an argument and return another function, but the concept is a bit more general than that, as we'll see. Coupled with this definition is a special syntax that lets you decorate functions with decorators. The syntax looks like this. This example applies the decorator, in this case named myDecorator, to the function named, in this case, myFunction. The @ symbol is the special syntax for applying decorators to functions. So what does this actually do? When Python sees decorator application like this, it first compiles the base function, which in this case is myFunction. As always, this produces a new function object. Python then passes this function object to the function myDecorator. Remember that decorators, by definition, take callable objects as their only argument, and they are required to return a callable object as well. After calling the decorator with the original function object, Python takes the return value from the decorator and binds it to the name of the original function. The end result is that the name myFunction is bound to the result of calling myDecorator with the function created by the def myFunction line. In other words, decorators allow you to replace, enhance, or modify existing functions without changing those functions. Callers of the original function don't have to change their code, because the decorator mechanism ensures that the same name is used for both the decorated and undecorated function. As with so many things in Python, a simple example is much more instructive than words. Suppose that we had some functions which returned strings, and we needed to ensure that these strings only contained ASCII characters. We can use the ASCII function to convert all non-ASCII characters to escape sequences, so one option would be to simply modify every function to use the ASCII function. This would work, but it isn't particularly scalable or maintainable. Any change to the system would have to be made in many places, including if we decided to remove it completely. A simpler solution is to create a decorator which does the work for us. This puts all of the logic in a single place. Here's the decorator. As you can see, the decorator, escape Unicode, is just a normal function. Its only argument, f, is the function to be decorated. The important part, really, is the local function wrap. Wrap uses the *args and kwargs idiom to accept any number of arguments. It then calls f, the argument to escape Unicode, with these arguments. Wrap takes f's return value, converts non-ASCII characters to escape sequences, and returns the resulting string. In other words, wrap behaves just like f, except that it escapes non-ASCII characters, which is precisely what we want. It's important to notice how escape Unicode returns wrap. Remember that a decorator takes a callable as its argument and returns a new callable. In this case, the new callable is wrap. By using closures, wrap is able to use the parameter f even after escape Unicode has returned. Now that we have a decorator, let's create a function that might benefit from it. Our extremely simple function returns the name of a particular northern city. And of course, we can see that it works. To add Unicode escaping to our function, we simply decorate Northern City with our escape Unicode decorator. Now when we call Northern City, we see that, indeed, non-ASCII characters are converted to escape sequences. This is, of course, a very simple example, but it demonstrates the most important elements of decorators. If you understand what's going on in this example, then you understand 90% of what there is to know about decorators. Now that we've seen how decorators work, let's look at how other kinds of callables can be used as decorators. We just used a function as a decorator, and that's probably the most common form of decorator in general use. However, two other kinds of callable are also used fairly commonly. The first of these is class objects. Remember that class objects are callable, and calling them produces new instances of that class. So by using a class object as a decorator, you replace the decorated function with a new instance of the class because the function to be decorated will be passed to the constructor, and thereby the initializer. Remember, however, that the object returned by the decorator must itself be a callable object, so the instance resulting from the constructor call must be callable, which means it must support the dunderCall method. That is, we can use class objects as decorators so long as the instance objects we get when we call the constructor are themselves callable by virtue of implementing the dunderCall method. In this example, we'll create a class callCount, which keeps track of how many times it's called. CallCount's initializer takes a single function f and keeps it as a member attribute. It also initializes a count attribute to 0. CallCount's dunderCall method then increments that count each time it's called, and then calls f, returning whatever value f produces. You use this decorator much as you might expect, by using @callCount to decorate a function. Now if we call hello a few times, we can check its call count. So now we've seen how to use class objects as decorators. Another common kind of decorator is a class instance. As you might have guessed, when you call a class instance as a decorator, Python calls that instance's dunderCall method with the original function and uses dunderCall's return value as the new function. These kinds of decorators are useful for creating collections of decorated functions which you can dynamically control in some way. For example, let's define a decorator which prints some information each time the decorated function is called. First, here's a class. But let's also make it possible to toggle this tracing feature by manipulating the decorator itself, which we'll implement as a class instance. Remember that, unlike in our previous example, the class object itself is not the decorator. Rather, instances of trace can be used as decorators, so let's create an instance of trace and decorate a function with it. Now if we call rotateList a few times, we can see that tracer is doing its job. We can now disable tracing simply by setting tracer.enabled to false. And we see that the decorated function no longer prints out tracing information. The ability to use functions, class objects, and class instances to create decorators gives you a lot of power and flexibility. Deciding which to use will depend a great deal upon exactly what you're trying to do. Experimentation and small examples are a great way to develop a better sense of how to design decorators. In all of the examples we've seen so far, we've used a single decorator to decorate functions. However, it's entirely possible to use more than one decorator at a time. All you need to do is list each decorator on a separate line above the function, each with its own @ symbol, like this. When you use multiple decorators like this, they are processed in reverse order. So in this example, sum function is first passed to decorator 3. The callable returned by decorator 3 is then passed to decorator 2. That is, decorator 2 is applied to the result of decorator 3 in precisely the same way that it would be applied to a normal function. Finally, decorator 1 is called with the result of decorator 2. The callable returned by decorator 1 is ultimately bound to the name sum function. There's no extra magic going on, and the decorators involved don't need to know that they're being used with other decorators. This is part of the beauty of the decorator abstraction. As an example, let's see how we can combine two decorators we've already seen, our tracer and our Unicode escaper. First, let's see the decorators again. And now let's decorate a single function with both of them. Now when we use this to invent names for Norwegian islands, our non-ASCII characters will be properly escaped and tracer will record the call. And of course, we can disable the tracing without affecting the escaping. So far, we've only seen decorators applied to functions, but it's entirely possible to decorate methods on classes as well. In general, there's absolutely no difference in how you use decorators for methods. To see this, let's create a class version of our island maker function and use the tracer decorator on it. We can also use this to cross the North Sea and make a more British version of our island maker. As you can see, tracer works perfectly well with methods. Decorators replace a function with another callable object, and we've seen how this can be a powerful technique for adding functionality in a modular, maintainable way. There's a subtle problem, however, with how we've used decorators so far. By naively replacing a function with another callable, we lose important metadata about the original function, and this can lead to confusing results in some cases. To see this, let's define an extremely simple function. In the REPL, let's look at some attributes of this function. First, it has an attribute dunderName, which is simply the name of the function as the user defined it. Similarly, it has an attribute dunderDoc, which is the doc string defined by the user. You may not interact with these attributes a lot directly, but they are used by tools like debuggers and IDEs to display useful information about your objects. In fact, Python's built-in help function uses these attributes. So far so good, but let's see what happens when we use a decorator on our function. First, let's define a simple no-op decorator. And now let's decorate our hello function. All of a sudden, help is a whole lot less helpful. Instead of telling us that hello is named hello and reporting the expected doc string, we're seeing information about the wrapper function used by the no-op decorator. If we look at hello's dunderName and dunderDoc attributes, we can see why. Since we've replaced the original hello function with a new function, what dunderName and dunderDoc attributes we get when we inspect hello are those of the replacement function. This is an obvious result in retrospect, but generally not what we want. Instead, we'd like the decorated function to have its original name and doc string. Fortunately, it's very easy to get the behavior we want. We simply need to replace the dunderName and dunderDoc attributes of our noOpWrapper function with the same attributes from the wrapped function. Let's update our decorator to do this. Now when we examine our decorated function, we get the results we want. This works, but it's a bit ugly, and it would be nice if there were a more concise way of creating wrapper functions which properly inherited the appropriate attributes from the functions they wrap. Well, we're in luck. The function wraps in the functools package does precisely that. Functools.wraps is a function decorator which you apply to your wrapper functions. The decorator takes the function to be decorated as its argument, and it does the hard work of updating the wrapper function with the wrapped function's attributes. Here's how that looks. If we now look at our hello function in the REPL one more time, we can see that indeed everything is as we want. As you start to develop your own decorators, it's probably best to use functools.wraps to ensure that your decorated functions continue to behave as your users expect. We've seen how to use and create decorators, and hopefully it's clear that decorators are a powerful tool for Python programming. They are being used widely in many popular Python packages, so it's very useful to be familiar with them. One word of warning though. Like many powerful features in many programming languages, it's possible to overuse decorators. So use decorators when they are the right tool, when they improve maintainability, add clarity, and simplify your code. If you find that you're using decorators just for the sake of using decorators, take a step back and think about whether they're really the right solution. One interesting and practical use of decorators is for validating function arguments. In many situations, you want to ensure that function arguments are within a certain range or meet some other constraints. Let's create a decorator which verifies that a given argument to a function is a non-negative number. This decorator is interesting in that it takes an argument. This might appear confusing at first, but you'll see how it works if you just follow the description of decorators which we just finished covering. Here's how you can use this decorator to ensure that the second argument to a function is non-negative. We can see that it works as expected. So how does this decorator work? First, we need to recognize that check non-negative is not, in fact, a decorator at all. A decorator is a callable object that takes a callable object as an argument and returns a callable object. Check non-negative takes an integer as an argument and returns a function, the nested validator function. What's going on here? You'll see that at the point where we decorate createList, we actually call check non-negative. In other words, the return value of check non-negative is the actual decorator. Python takes check non-negative's return value and passes our function createList to it. Indeed, if you look at the validate function by itself, you'll see that it looks exactly like the other decorators we've defined in this module. Interestingly, the wrap function returned by validator forms a closure over not just f, the decorated function, but also over index, the argument passed to check non-negative. This can be a bit of a mind bender, and it's well worth spending a little extra time to make sure you really understand how this works. If you understand this example, you're well on your way to mastering Python decorators. To close out this module, let's review what we've covered. Def is executed at runtime. Def defines a function in the scope in which it's called, and this can be inside other functions. Functions defined inside other functions are commonly called local functions. A new local function is created each time the containing function is executed. Local functions are no different from other local name bindings and can be treated like any other object. Local functions can access names in other scopes via the LEGB rule. The enclosing scope for a local function includes the parameters of its enclosing function. Local functions can be useful for code organization. Local functions are similar to lambdas, but are more general and powerful. Functions can return other functions, including local functions defined in their body. Closures allow local functions to access objects from scopes which have terminated. Closures ensure that objects from terminated scopes are not garbage collected. Functions with closures have a special dunder closure attribute. Local functions and closures are the keys to implementing function factories, which are functions that create other functions. Function decorators are used to modify the behavior of existing functions without having to change them directly. Decorators are callable objects which accept a single callable object as an argument and return a new callable object. You use the symbol to apply decorators to functions. Decorators can enhance maintainability, readability, and scalability of designs. Decorators can be any kind of callable object. We looked specifically at functions, class objects, and class instances. The dunder name and dunder doc attributes of decorated functions are actually those of their replacement function, which is not always what you want. You can manually update the dunder name and dunder doc attributes of your wrapper functions. The functools.wraps function can be used to create well-behaved wrappers in a simple and clear manner. Multiple decorators can be applied to a function. When there are multiple decorators, they are applied in reverse order. Decorators don't have to be specially designed to work with other decorators. Decorators are a powerful tool, but make sure you don't overuse them or use them unnecessarily. There is technically no such thing as a decorator that takes extra arguments. To parameterize decorators, you need a function that creates decorators. Local functions can create closures over objects in any number of enclosing scopes. Thanks for watching, and we'll see you in the next module.